In this video, we're going to look at writing some net ionic equations and doing some calculations with acid-base reactions. Now, we've talked about general definitions of acids and bases, that an acid donates or produces hydrogen, a base can accept hydrogen, or it might produce hydroxide in solution. This Bronsted-Lowry definition, that's not such a big deal anymore. This idea about acids and bases being proton donors and acceptors. The AP test is kind of leaning toward using the Arrhenius definition, focusing more on hydrogen in solution and less on it being protons transferred. But technically a hydrogen ion is a proton. So that's why they have it in there, but I wouldn't worry so much about the Bronsted-Lowry definition of acids and bases. I'd focus more on hydrogen. Now, when you start writing a net ionic equation, I usually start it off like a first-year chem equation. I write the formulas, and then I want to do some kind of like a replacement, see what's produced, and then I'll look for any spectator ions. Can I trim this down to any kind of a net ionic equation? It says here, watch out for weak acids and bases. And that usually causes some concern because people are like, I don't want to memorize all the weak acids and bases. Don't. Instead, remember the strong acids and bases. They're much more common. We use them way more often than some of these weak acids and bases. I would know that hydrochloric, nitric, sulfuric, and that hydrogen chloride. Those are the most common strong acids. Strong bases, a soluble hydroxide, most commonly sodium or potassium hydroxide. So the first time I want to attack this reaction, I'm just going to write the formulas. So I see acetic acid and potassium hydroxide. So I want to go acetic acid, or I could write it as hydrogen acetate, H3O2. Your other option with acetic acid would be to kind of write it this organic way, CH3COOH. It's totally acceptable. The hydrogen that we're going to lose is either this guy, or here it's kind of dangling off the end. This organic structure kind of matches its true molecular model, where there's a carbon surrounded by 3 hydrogen, then comes another carbon. There's a double bonded oxygen and a hydroxide group. It's this guy that we're going to lose. So either way is totally fine. Sometimes I think it might be a little easier to write it as hydrogen acetate, then you know which hydrogen you're going to lose. What else do we got here? Potassium hydroxide, KOH. All right, awesome. So the first time I write this, let's just do it as a double replacement. A lot of acid-base reactions really are just double replacements, where I'm going to switch maybe the hydrogen and the potassium. So one of my products will become potassium acetate. And what do you know? Hydrogen hydroxide, aka water. And I could care less which way you want to write it. If you leave it as hydrogen hydroxide, that is perfectly acceptable. If you change it to water, not a problem. Everybody will know what you're talking about. Okay, so here's the equation. It's all 1-to-1 ratios. It's all +1, -1, so I don't have to worry about any coefficients. But now let's say I want to scale this down to net ionic. I'm looking for spectator ions, which means I want to dissociate anything that can extensively ionize. That's a mouthful. In other words, anything that's a strong electrolyte, which is ionic compounds, soluble ionic compounds, strong acids, and strong bases. Those I want to split apart into their ions. They would extensively ionize. Watch out for strong acids and bases and weak acids and bases. You kind of have to survey the scene here. Acetic acid is a weak acid. That means it does not extensively ionize. Out of 100 molecules, maybe only 1 splits into hydrogen and acetate ions. We do not get to split acetic acid. This guy stays together. It's a weak acid or a weak electrolyte. However, potassium hydroxide is a strong base. A strong base is a strong electrolyte. So I can think of this guy as like potassium and hydroxide ions. Those guys would split in solution. On the product side, I've got potassium acetate. This would be a strong electrolyte. Anything with potassium is a compound that will highly ionize in water. So we're going to split this guy into potassium ions and acetate ions. Highly soluble. O2 minus. Now I did put phase symbols in the first time through, and I suppose I could, and that may be helpful. This is aqueous. These are both aqueous. They're in solution. I just don't get to split the weak acid. It does not extensively ionize. On the product side, this potassium acetate will be a solution, a strong electrolyte, so it does extensively ionize. Water is a liquid. We do not get to ionize liquids, gases, solids, anything like that in an equation. I'm not even thinking about splitting for spectator ions. I'm really only looking for anything aqueous, and then it needs to be a strong electrolyte, a strong acid, a strong base, or something that is highly soluble in water, like potassium compounds. So I'm not even thinking about splitting that water molecule. That's together for life. So really, I only have one spectator here. If I look for things that are the same on both sides, the only spectator is this potassium ion. The hydroxide has to stay. On the product side, it turns into water. It's different. There are not free-floating hydroxide ions on the product side. Kind of the same deal with acetate. He's got to stay. The acetate ion on the product side is not the same as the acetate on the reactant side. It's with hydrogen on the reactant side, and it does not extensively ionize. So I really only have one spectator, just potassium. So my final net ionic would be the acetic acid, O2, we'll call that aqueous. The hydroxide ion, we'll say aqueous, he's in solution. I'm going to have the acetate ion, O2 minus, you are aqueous. And I got liquid water. And again, it doesn't matter if you write it as HOH, H2O. Nobody's going to care. That's my net ionic. This is the kind of stuff they're going to put on the AP test, and it stumps kids a lot. That strong acid, strong base distinction is really what they're looking for. Do you understand that a weak acid or a weak base does not ionize, but a strong acid or a strong base does? Check out this one with ammonia. Write the ionic equation for the reaction of hydrochloric acid, HCl, and ammonia. Now, ammonia is actually a gas, NH3, but in solution, if we're talking about like an ammonia solution, it actually exists as ammonium hydroxide. So these guys are kind of the same gig. Ammonia, NH3, is technically a gas, but an ammonia solution could be written as NH4OH, ammonium hydroxide. Now we could also write ammonia NH3 aqueous, but for purposes of writing a net ionic equation, I think this is going to be a little easier. So let's do this. Let's do this as a first-year chem equation. So we're going to do a double replacement. I can switch the positive or the negative ions. One of my products will be ammonium chloride, +1, -1. And there she is, HOH, hydrogen hydroxide. There's my water. And again, if I wanted to, I could put in these little phase symbols right away. These are solutions. Anything with chlorine, well, most things with chlorine are aqueous, except for silver, mercury, and lead. But anything with ammonium is aqueous, highly soluble, so there's no doubt on that one. And the water is a liquid. Alright, so kind of the same gig as above. Now let's scale this down to net ionic. We're looking for anything that can extensively ionize. Yes, HCl is a strong acid. You get to split into hydrogen and chlorine ions. Ammonia is a weak base. You do not get to split a weak base. Again, maybe only 1 out of 100 ions will actually split. On the product side, we said this ammonium chloride is highly soluble. So yes, we get to split this guy into ammonium and chlorine ions. But no, we do not get to split water. Water's together for life. So again, I'm looking for any ions that are the same on both sides. And there is only one, just chlorine. So my net ionic, I'm going to have the hydrogen ion. I'm going to keep this guy together, NH4OH. And we can put phase symbols in. We'll call these aqueous. They're in solution. Da-da-da. On the product side, I'm going to have the ammonium ion, aqueous, and water. Liquid. You do not get to split the water. There she is. Now, a lot of times on the AP test, they will give you these examples. Acetic acid is the most common weak acid. You know, something like ammonia is the most common weak base. So don't try to memorize all these strong acids, weak acids, strong base, weak base. I would just know the common ones. That's what they're going to focus on. They want to know, are you aware of the fact that a strong acid dissociates completely, and in this case a weak base does not? That changes what my net ionic equation will look like.